Okay, in continuing on with diagonalization, now we just looked into looking at whether 2 by 2 matrices of certain types were diagonalizable, and now we have crossing over to 3 by 3 matrix, and we have in this example we have A is equal to this particular 3 by 3 matrix. First column we have 4, 2, 2. Second column we have at 2, 4, 2. And the elements in the third column we have at 2, 2, and 4. And we have given that the eigenvalues are at 2 and 8. And to see if this matrix is diagonalizable, and we have for the first eigenvalue 2, okay, so if I take A minus lambda I, or in this case A minus 2I, A minus 2I becomes, okay, nothing but 2's running across. And taking the difference, A minus 2I, quantifying and multiplying by x, setting equal to 0, and establishing what we have with the augmented matrix. And we have for the reduced echelon form, okay, so we end up with 1, 0, 0, 1, 0, 0, 1, 0, 0, and zeros exclusively in the last column. So the second and third rows are going to be nothing but zeros, and we have for the general solution, okay, this will come from the top row, from which we have x of 1 plus x of 2 plus x of 3 is equal to 0, and for what we have here, x of 2 and x of 3 are going to be free variables, whereas in the case of x of 1, we have equal to the negative of x of 2 minus x of 3. So we have for the solution in x, we have x of 2 times the vector negative 1, 1, 0, plus x of 3 times the vector negative 1, 0, and negative 1. So now for this particular case, now 2 is going to be a repeating eigenvalue. And what I mean by this is that it has more than one eigenvector for its basis. And we have as a basis for the eigenvalue lambda is equal to 2. Okay, we have from x of 2 and x of 3. We can say that for the first eigenvector, we have at negative 1, 1, 0. And for the second eigenvector, we have negative 1, 0, and 1. Okay, so you have two eigenvectors from this one eigenvalue of 2. Now, as for the other eigenvalue, which we have at 8, okay, now 8, for the eigenvalue of 8, A minus 8I, we have the difference going column by column. We have at negative 6, 2, 2. Second column we have at 2, negative 6, 2. Last column we have at 2, 2, and negative 6. And now taking what we have here in the difference, quantifying, multiplying by x, and setting equal to 0, and solving for x, now we have with the augmented matrix that is developed. Okay, this is going to reduce to where we have x of 1, x of 2, and x of 3 are all going to be 0. So there's not going to be any linearly, or I should say, there's not going to be any free variable. Okay, and so in this case, there's no eigenvector. Since there's no free variable, there'll be no eigenvector corresponding to the eigenvalue of 8. So we have in the predicament, okay, that is drawn forth, there are only two linearly independent eigenvectors, and those are the ones that we had to correspond with lambda equal to 2. Okay, so those are the only two linearly independent eigenvectors for A, which has 3 rows and columns. And so, so there's a deficiency in the number of linearly independent eigenvectors, and so we have in consequence A is not diagonalizable. All right, now, okay, so we strike out in this particular case. Now, to see if we have any better luck with this particular matrix A, another 3 by 3. Now we have eigenvalues at 1, 2, and 3, and we have for lambda equal to 1. So you have A minus 1I or A minus I. So we have negative 2, negative 3, negative 3, 4, 3, 1, negative 2, 0, and 2. And again, you have deduction of 1 from A, going from the upper left to the lower right diagonal, taking away 1 at a time. And for this difference times x equal to 0, again, expressing as an augmented matrix, okay, we have reduction to where the first row we have 1 0 negative 1 0, second row we have 0 1 negative 1 0, and with the third row consisting of zeros exclusively. This will signify the x of 3 is free. From the top row, we have the x of 1 is going to be equal to x of 3. For the second row, we're going to have the x of 2 is equal to x of 3. And so we have from this combination, it's going to follow that for x. We say that is equal to x of 3 times 1, 1, and 1. So we have a basis for the first eigenvalue, lambda equal to 1. We have the eigenvector 1, 1, and 1. Now for lambda equal to 2, okay, we have our a minus 2i. So we have negative 3, negative 3, negative 3, followed by 4, 2, 1. And the last column we have negative 2, 0, 1. And taking this difference, multiplying by x, setting to 0, and expressing as an augmented matrix. We had the augmented matrix in reduction form or reduced form, okay, to end up at going row by row. We have 1 0 negative 2/3 0, so this will signify that x of 1 is equal to 2/3 x of 3. Second row we have 0 1 negative 1 0, which will signify that x of 2 is equal to x of 3, with zeros exclusively at the bottom. Okay, this will signal that x of 3 is free. So we have the x is equal to x of 3 times 2/3, and also times 1. And again, with x of 3 is a free variable, we can insert the 1 at the bottom. And so we have alongside, okay, the variable coefficient x of 3. Okay, we have the basis for lambda is equal to 2, which we can say we have at 2/3, 1, and 1. And looking for what we have for the third eigenvalue 3, we have a minus 3i, so we had this 3 by 3 difference, and taking the difference, multiplying by x, and setting equal to 0, we have in establishing as an augmented matrix, we had the reduced form to be at 1 0 negative 1/4 0, 0 1 negative 3/4 0, and we have again zeros running across. So we have from the top row, we're going to have the x of 1 is equal to 1/4 of x of 3. From the second row, we had the x of 2 is equal to 3/4 of x of 3. And again, x of 3 is a free variable. And we can say that for the solution in x in this case, we have x of 3 times, okay, the vector 1/4, 3/4, and 1. And from this, okay, we can say that a basis for lambda equals 3 will be our third eigenvector, which we can label as 1/4, 3/4, and 1. And so we have 3 eigenvalues, 3 eigenvectors. And for what we have in the case of p, we have v of 1, v of 2, v of 3, which we can express as 1, 1, 1, 2/3, 1, 1, 1/4, 3/4, and 1. Okay, so you have first, second, and third eigenvectors, and just running diagonally, okay, just going eigenvalue by eigenvalue. So we have amongst the zeros, we have in the upper left-hand corner, we had the first eigenvalue 1. In the middle, we had the second eigenvalue 2. And in the bottom right, we have the third and last eigenvalue, which we had to be at 3. So this will be our diagonal, and in this particular case, you can check for the consistency to see if a times p is equal to p times d, and kind of running it through the computer or the calculator. Okay, a times p, we have a 1, 1, 1, 4/3, 2, 2, 3/4, 9/4, 3. And the same thing we had to apply for p times d, so there is consistency. So for what we have for p and d, those are verified.